No. Are you kidding?
We have
Really?
yeah, next fall, I believe, they're starting classes a day earlier so that we get Wednesday off on Thanksgiving week. So starting next fall. What's up?
No, I was telling him I'm not gonna do this. It's not really gonna benefit me. I got a loud voice. My bad.
Yeah, next semester or next
Wednesday
fall,
classes.
will start one day early, and then we'll get Wednesday off as well. I would have probably said, yeah, let's take Wednesday off if we weren't trying to cram all of this information into the very end. But we don't have time. I will not have a quiz on Wednesday, so if you do have to leave early to travel or anything, we won't have a quiz, but we will. I won't have a quiz on Wednesday. If you have to leave for travel, you can watch Echo if necessary. However, we have to first. Let us finish.
Nobody else comes.
TCA cycle. The last thing we did before class, we kind of crunched numbers and we looked at exactly up until this point from one glucose what has been produced following aerobic pathways. First two aerobic glycolysis is not an aerobic pathway. The formation of pyruvate gives us a choice, and under aerobic conditions, it's one part of the TCA cycle. So for one glucose, we decided we have 4 NTPs, 2 ATPs and 2 GTPs, or 4 ATPs, 10 NADH and 2 FDH2. That's what we saw, right? The other idea I wanted to talk about before we get into the steps of glycolysis, I guess first, from this figure, we're looking at the TCA cycle. From this drawing, can you tell which steps are reversible? Sure, right? You can tell which steps are reversible, right? Because you don't have reversible reaction arrows, right? What do you know about reversible steps in metabolic pathways? What do you know? Let's say reversible. I mean, to say irreversible. What do you know about irreversible steps? It can't go back. Therefore,
Can only go forward.
regulation occurs at irreversible steps. Regulation occurs at irreversible steps. There are 3 irreversible steps in glycolysis. Step 1, step 3, and step 10. So regulation occurs in the TCA cycle. Step 1, step 3, and step 4. Irreversible cycle. So regulation occurs at step 1, step 3, and step 4. Regulation also occurs conversion of pyruvate to acetyl-CoA. We did that, right? Yes. Regulation is also occurs at this step. The regulated step. Regulation occurs at irreversible steps 1, 3, and 4. Another idea I kind of wanted to talk about beforehand. Your textbook talks about this after the TCA cycle. I want to talk about it before the TCA cycle. Somebody asked, I don't know if it was somebody in this class or the Tuesday, Thursday class. Someone asked, do we need to be able to read metabolic maps? Is that one of you guys? Somebody emailed me and said, do we need to do this? Read metabolic maps. I'm like a great professor, I didn't answer. I wanted to talk about it in here. I wanted to talk about it in class. I want to email. Do we need to be able to read metabolic maps? Hopefully you've seen a metabolic map. Have you seen a metabolic map in your textbook? 3 people shaking their head and everybody else looking at me like, I have no idea what a metabolic map is. So perhaps we shall look at one. A metabolic map is a very, very confusing set of lines and words. That's pretty much what it is. If you look in your text, both texts are going to have various pictures of metabolic maps. I bet the Linenger one is going to be a little more cartoony. The Linenger one's probably going to be a little more cartoony than the Biochem one. This is good. Here's a really great cartoon. So here's a picture of a metabolic map with terrible resolution. Oh, there it is. Yeah, here's a nice cartoony metabolic map. I'm showing you the idea of a metabolic map is to show you what pathways are connected to which steps of the metabolic pathways. It's to show you and demonstrate that pretty much all metabolic pathways are connected somehow. The main idea of a metabolic map is showing you those things, but also the fact that right in the middle of it is glycolysis and the TCA cycle. It looks like a nice thermometer right in the middle of your metabolic map. I like this cartoon one because it's easy to read. More complete ones. Complete one. And if you know that, you should be prepared for your. I'm just kidding. Prepared for your exam. It does look very confusing, but you can see the same way. It's not drawn as nice and cartoony, but glycolysis is coming right down the middle until you get pyruvate and enter the TCA cycle, and it shows you what is connected to what step of this TCA cycle is connected to something else. The main idea that I want you to take from this is that glycolysis and the TCA cycle, yes, they go hand in hand, and we talked about how one transitions to the other. However, at every single step of glycolysis, at every single step of TCA, these intermediates are not going from A to B to C to D to E F to G. They're going from A to B, and then B is being pulled on by 20 other different pathways. And then B goes to C, and C is being pulled on by 10, 5, 20 different other pathways. There are many other things drawing citrate away, drawing isocitrate, alpha-ketoglutarate away, succinyl-CoA, succinate, fumarate, malate, oxaloacetate. There are many different pathways pulling on all of these. It's not just going in this direction, and every single step is branching out. Other processes, anabolic synthesis processes, are pulling on these materials to build other things as well. Some of the main ones that you should probably know: citrate. Citrate. The production of fatty acids. Isocitrate. We'll talk about isocitrate in a minute. We'll see kind of why we're going to leave it off the list. Alpha-ketoglutarate is a main precursor for glutamate. Other amino acids as well, mainly glutarate, and purine bases. Succinyl-CoA, very prevalent in the formation of porphyrin rings. Porphyrin rings contain iron, they're called heme. So ultimately, it's involved in the formation of hemes, and directly involved in the formation of porphyrin rings. Malate involved in the reverse direction, and this is an irreversible reaction. Right? However, we'll go back to pyruvate comes from malate. This step would not be necessary if this was a reversible step. Not soil acetate, oxaloacetate. Nice turning point to go around and go from the TCA cycle back to gluconeogenesis, production of glucose, production of various amino acids. Pyrimidine bases. These are some of the main things drawing on the TCA cycle, other than subsequent steps of the TCA cycle, right? Subsequent steps in the TCA cycle are drawn on each step of the TCA cycle, pulling in a specific direction. However, it's also being pulled other ways by various other processes depending on current physiological needs. Does that make you want to take metabolism and regulation? Take MetReg. This is MetReg. You go through all of this. A whole semester. It is a good class. You must be confident. Okay, step 1. Perkin condensation. The formation of citrate. Step 1, formation of citrate. So this is a Perkin condensation. Perkin condensation. Does anybody remember what a Perkin condensation is? Did anybody even learn what a Perkin condensation is? Yesterday, everybody told me we did not learn in organic chemistry what a Perkin condensation is. No?
No.
You did not learn what a Perkin condensation is. You learned what a placing condensation is. Yes. Anybody know what a placing?
I don't know.
Everybody said no yesterday as well, which is great. I'm glad you're doing it. No? Okay. A Perkin condensation is like a placing condensation. And if your text doesn't think to limit your text and call this a placing condensation, guess what? It's wrong. It's not a placing condensation. This is a Perkin condensation. Formation of a CC bond. Formation of a CC bond between an ester and a ketone, or an ester and an alcohol. Could be an alcohol. No, in this case, we're ketone. We're actually not working with ester, we're working with bioester. Bioester. So what is this? This is acetyl-CoA. Here's our bioester. Acetyl-CoA and acetyl-CoA. Oxaloacetate.
The batteries go out? Huh?
So my kids got sick last night. 2 of them. One of them came and got in bed with us. I thought he peed in the bed. And he didn't. He was sweating so bad. Running a fever. And I was all excited this morning. I was like, because our kids are sick. Kids are sick. That means I get to stay home and play video games all weekend and have a reason to sit in bed and play video games with my kids. That's terrible. So it is what it is. Okay, Perkin condensation. So I'm very tired today because I was out all night. 2 sick. All night. It's awesome. Perkin condensation. Leaves us with an intermediate. And we're not going to draw every single step of all of these reactions because they're in your textbook. CoA intermediate. Hydrolysis at the ester position. Leave us with citrate. And we're going to draw starting material, we're going to draw finishing material because after we're done with all of these steps, I want to talk about isotopic labeling and how it works, how it's used, and how you follow it. Cool little experiment. So we have acetyl-CoA. So plus, I'm going to draw. So this is, it's a little confusing. So when we draw these, I'm going to actually draw them different in each step. So when we draw citrate here and citrate on the next page, I'm going to draw them slightly differently because chemistry is happening at different places each time. So it may be a little tough to follow, but we'll try to do our best. This reaction is catalyzed by an enzyme called citrate synthase. Form citrate. Bless you. Kind of, hopefully from our drawing you can see what's happening. Enzyme, citrate synthase. What is a synthase? I've told you I'd like you to know what these enzymes do because it kind of it's a shortcut for the reaction mechanism. You know what synthase is. And the name of the enzyme, you can tell what is happening at that step. So that's nice. So what is a synthase? A synthase catalyzes a condensation reaction. So specifically, it's acid. So this synthase synthesizes a condensation. Now, nucleoside phosphate. And remember I told you if you like to say nucleotide phosphate, that's fine, you can say that. You can be wrong if you want to, it doesn't matter. Correct nomenclature is nucleoside phosphate. ADP, ATP, GDP, GTP. Synthases are condensation reactions that are not coupled to phosphoryl transfer, not coupled with nucleoside triphosphates or nucleoside diphosphates. I think the literature text talks about this, but they kind of talk about it force blinders on, if you know force blinders on. Horses have to wear so blinders in the race, but they have to put them on so they're not distracted by anything else. They only see this one thing and they go that way. Your book kind of does that, and it says, this is what happens. It's not just that. That is a possibility of what could happen with the synthase. They're bigger than that. The better definition is condensation reactions. Nucleoside phosphates in general, not just ATP. Nucleoside phosphates. We'll talk about synthetase reactions, condensation reactions involving these, which is really easy because if you look at the enzymes involved in the steps of the TCA cycle, there is only one step that generates ATP, and do you think that's going to be a synthase or a synthetase? Synthetase, because those enzymes are condensation reactions involving GDP. Hopefully it helps you not have to memorize every single step. It's happening every single step. Identify enzymes, nomenclature from enzymes helps a lot. Citrate synthase is a homodimer. What does that mean? Two of the same subunits, right? So two identical subunits, two of the same polypeptide chains. And here's one little, we call it a big unique piece of information. How many substrates does this enzyme have? Two, right? We have two substrates. Enzyme binds acetyl-CoA, enzyme binds oxaloacetate. Binding oxaloacetate induces LCC, a large conformational change. Binding oxaloacetate induces a large conformational change, which facilitates acetyl-CoA binding. Now I will give you the definition of cooperative binding. Binding at one subunit facilitates binding of the same substrate at a secondary or tertiary subunit. This is not cooperative binding, right? This is not cooperative binding. This is not binding of a substrate at one subunit, increasing binding of an identical substrate at an identical binding site, well, not really identical, conformational change, right? At a similar binding site on a different subunit. This is binding of one affecting binding of the other. What do we call it? It is that ordered thingy. That will not be one of your multiple choice answers. If this question is asked on your exam, that ordered thingy will not be on there, I promise you. Could you think of another way to word it that may be on there? Ordered by substrate, that's perfect. Ordered by substrate, sequential binding, sequential by reaction, sequential by substrate. So ordered or sequential by substrate reaction, right? This would follow an ordered mechanism. If I ask you to draw, let's say, a Langley-Burke for an ordered by substrate, which Langley-Burke do you think it would follow? You know it's ordered by substrate. Remember when we drew Langley-Burke's? Why do you draw Langley-Burke? Because you can tell differences in Km and Vmax easily, right? This is ordered by substrate. Would you think? Well, obviously, if we change the amount of substrate, we're going to affect Vmax, right? Would this affect Km? Yes, because changing the concentration of one is going to change the concentration of binding on the other, right? So it would affect Km. So if I gave you some graphs of Langley-Burke plots and asked which one do you think this would follow, you would assume that it would change both Vmax and Km, right? Both Vmax and Km. And we said a second ago this step is regulated. This is a regulated step. And hopefully at this point, we've talked about 3 regulated steps. We just talked about a 4th up here, pyruvate to acetyl-CoA. Hopefully at this point, you're starting to see a trend here. Regulated steps. What regulates these steps in a positive manner? What regulates these steps in a negative manner? Most of these steps, they have similar modes of regulation. And the fact that anything that signals we don't have enough energy activates. Anything that signals we have enough energy deactivates. So a positive regulator, something that tells it we don't have enough energy, something like ADP, would be a positive regulator. A negative regulator would be something like ATP. ADH. And these aren't the only ones. The one that I will talk about is citrate. That should turn a light on. What do we call this? Product inhibition, right? Because citrate is the product for this reaction, right? Citrate is the product for this reaction. This is also inhibited by acetyl-CoA, which is a subsequent step along the pathway, which also makes sense. We've seen that before, right? We've seen specific enzymes being inhibited by not precursors, but I don't know what you call subsequent steps, subsequent products in the chain. We've seen that before, right? We saw step 3 of glycolysis being inhibited by step 1, citrate, right? Being inhibited by citrate of the TCA cycle. So subsequent steps along this metabolic chain can inhibit the previous steps. That makes sense. But the fact that this is inhibited by citrate it's unique. Remember, I told you it's not really rare, but it's not common. Features product inhibition. Step 2. Step 2 uses an enzyme called the conipase. Kinase is studied in reaction 2 is a two-step isomerization reaction. So when somebody says something, right? Somebody says, we know a lot about this enzyme, we've studied it. We know a lot about this protein, we've studied it. That should tell you two things. One, it's either extremely important and easy to come by, or two, it does something pretty weird. It's kind of odd, it's an oddball. So two things, because there's only one way to get published. I guess there are two ways to get published. You publish something that's very important, or you publish something that's flashy. That people want to read about, that makes people interested. Like, that's weird, I'll read about that. I don't know why, but people like to hear things that aren't normal, right? People like to read things that intrigues them. So we'll talk about this reaction. It's catalyzed by a conatase. This enzyme pretty much catalyzes the reaction of citrate to an intermediate. So here's the catalyzed by a conatase, a reaction converts citrate to a conatase. Remember, if we go back to the step before, our overall reaction mechanism, I said this is a step 2 is a dehydration and then a rehydration. 2 steps, dehydration. We're going to remove water, we're going to put it right back in. So it's a dehydration of citrate, we're removing water. We're left with an conatase. Conatate. We're left with an intermediate conatate using the cis combination. And at this point, our enzyme converts citrate to an intermediate, a stable intermediate. And at this point, our enzyme is going to reinsert that water, and where it inserts that water matters. It leads to 2 products. Where it inserts the water leads to 2 products. Most likely, what is going to happen? Most likely, it is going to insert that water exactly where it took it from. If you look at reaction arrows, most likely, you take this enzymatic reaction out of a metabolic pathway, and you do this in a test tube. This enzyme is going to look like it does not do anything. 90+% of this is going to go right back to citrate. It's going to look like, wow, this enzyme is not even active. It doesn't do anything. Why? Because it favors citrate. Favors this direction. Favors this direction. However, to a small extent, you will also insert water. Secondary place, a little bitty arrow, because to some extent, anywhere from 3 to 10%, it will produce your favorite product. I say favorite product. Favorite product for the TCA cycle. It will produce isocitrate. It will produce isocitrate. So why, under physiological conditions, does this reaction move towards isocitrate? Removal of product, right? It's in a metabolic pathway. It's in a sequential pathway. As soon as we make isocitrate, guess what's going to happen to isocitrate? It's going to follow the next step, right? The next step is a pretty fast step. So as soon as we have isocitrate, it's going to be pulled away, so it's going to drive the reaction to the right. Hopefully, these terms are starting to make sense, right? Removal of product. This is why it was a bullet point in chapter 17. 3, where we're at. So this reaction now is much more prominent. Removal of product. So our red arrows would probably represent what's happening in a test tube, and an organism. Our green arrows would be a better representation. And you know it's not a mathematical representation. Drawing is the scale of the image. Our enzyme this unique bind. That's pretty unique. It's an enzyme that goes forward in a metabolic process, but in a test tube, it doesn't do anything. In laboratory conditions, it doesn't. It looks like it's inactive. It looks like you have an inactive enzyme that doesn't do anything. Put it in a process in which you're drawing products away. This enzyme has a distinct cofactor that has a 3-iron, 4-sulfur cluster, and a roughly cubic. So whoa, that's not enough edges to make it. Enough points. Right? You're right. There's an open coordination site in this cluster. It needs to be further activated. If you take NetReg, you'll talk about this enzyme aconitase as an iron regulation step in cells. It is an iron regulation step. It's iron sensitive, and it's also going to draw in more iron from the solution. So what does this 3-iron, 4-sulfur cluster look like? Imagine you're going to draw a big open circle here. There's our open coordination site. We can bring something into bind. So yeah. This active site cluster is held together by cysteine residues. Iron. So we have an enzyme, we have cysteine residues holding our active site. Our active site iron sulfur cluster in place. This isn't the only iron sulfur cluster we're going to talk about. Our substrate coordinates directly to iron sulfur cluster. However, this is an inactive form of our enzyme. Our enzyme, this is an inactive form. Not only does it have an iron sulfur cluster, this is also a metal-dependent enzyme. It needs a metal cofactor. So it is going to pick up metal from solution. Iron 2+ cation. So this is an iron-activated enzyme. It requires a metal cofactor. This metal cofactor covalently binds to our substrate on the enzyme substrate complex. Substrate citrate. Will bind to a water. You see this common metals in proteins will commonly, so metals like iron, it wants to be coordinated to 5 to 6 things. Iron, that's what iron does. If you've taken inorganic, you probably know this. If you haven't taken inorganic, you don't have time to know this. But metals will frequently coordinate to 4, 5, and form 4, 5, and 6-membered coordinate structures. Iron specifically likes to form 5-membered structures, or 5 coordinate structures, or 6 coordinate structures. So iron picks up the water, picks up the site, and then bind to citrate. Citrate, completely different than we just did a second ago. You may have to go back and look at this to follow exactly which carbon is which carbon. It's just possible. We have interaction here, but it's not really a bond. Your textbook may draw it as a bond. It's not really a bond. It's within bonding distance. Kind of a long bond. It's not happening. I drew that hydrogen. Hydrogen doesn't do that, does it? There we go. Oxygen, not hydrogen. There is an amino site residue acts as a general base to initiate this process. extracting a proton. Right? So we gotta lose the water, that's why I drew my H and my OH in blue. Here's the water that I'm losing. We're working towards an econotate intermediate. In our econotate intermediate, this proton is abstracted by an active site residue acting as a general base. Leave now coordinated to our iron, which leaves us with an intermediate. Leaves us with a non-enzyme bound intermediate. That one step. Sulfur cluster is going to release our enzyme, or our substrate, I'm sorry. Sulfur cluster is going to release our substrate, leave us with an intermediate. Remember we said this is very reversible, right? It's going to form our intermediate. We can easily insert that water right back into the exact same position. Use water here. We reinsert it, we gain that water right back. So, what are options? We said in normal conditions, this reaction arrow will look something like so, right? In normal conditions, this reaction doesn't look like it goes forward. It looks like this water is inserted right back into the exact same position. Under physiological conditions, this is in a metabolic pathway that's being pulled on in different directions. It is being pulled on significantly enough in the direction to the right, so we are forming a significant amount of isocitrate. Add our water right back in. The world is different. Hydroxyl group moves. Leave us with isocitrate. Citrate going to isocitrate. We have 12 minutes. We are going to finish the next two steps. Without a doubt, we're going to get through 4. Isocitrate, next step, is oxidized alpha ketoglutarate. Isocitrate is oxidized to alpha ketoglutarate. Guess what type of enzyme this is going to be? Oxidative reductase, right? It is isocitrate dehydrogenase. So far, every single dehydrogenase we've talked about has been coupled with what cofactor? What? NAD, right? NAD, an electron shuttling cofactor, an electron transport cofactor. Isocitrate dehydrogenase is coupled to NAD in every single dehydrogenase enzyme we talked about, every dehydrogenase we talked about so far. Isocitrate dehydrogenase has various isoforms. All those isozymes, different isoforms. These different isoforms actually regulate whether this is an NAD dependent enzyme or an NADPH or an NADP enzyme. So various isoforms determine whether it requires NAD or NADP. We talked about what's the role of NADP? Why NADP? Why not NAD? Why would we need NADPH as opposed to NADH? We've already talked, you know where NADH goes, right? Where does NADH end up going ultimately? ATP, right? We're going to oxidative phosphorylation, respiratory phosphorylation. We're going to produce ATP eventually. That's the end goal. What's the end goal of NADPH? Do you know? Did we talk about this? I think I said it like very briefly. I mean, I said it one time. That was it. NADPH. It's part of anabolic processes, anabolic biosynthetic processes. In catabolic processes, we're generating NADH for the purpose of producing ATP. In anabolic processes to produce our big molecules, the same way we're breaking down in catabolic processes, and it requires an NADPH. So this can turn on or off production of energy, or we need energy to produce build other structures. Different isoforms can determine what product this is going to spit out. So we are under the assumption that we need energy. Yes, absolutely. Thank you. We're under the assumption that we need energy. So if we need energy, we're going to draw the rest of this reaction, assuming we're using an isoform that requires NAD. But that's not the only possibility, right? Instead of spitting out, so if we go back here, this NADH could be 8, which would add 2 NADPH, right? And this could be 8, which would give us 2 NADPH. So if you remember when we talked about a brief overview of how many ATP can we possibly get out of the oxidative process, it was 30-ish, right? There's an ish because we don't know, right? We don't know exactly what's going to happen in every step. Best case scenario, maybe 38, 36, but it could be as little as 30. Whew. Okay, so that's a big key player. In glycolysis, the only option is production of ATP and production of NADPH. All of a sudden we get to the PCA cycle, we can directly yield NADPH, right? So it is a possibility, right? It is a possibility. We can yield NADH, we can yield NADPH in the TCA cycle. I promise you're going to have a question on your exam. You need to know that. It is a possibility. Why do we need NADPH? And what pathway can possibly generate it? Oxidation of alpha ketoglutarate. I take back what I said. We're only going to go through reaction 3. Reaction 4 is super quick though. Yes, I know I drew it different again. I apologize. Like I said, after class, you may have to go back through here and be like, is that really isocitrate? How did it change? What group is what? Oh, that carboxyl group you drew right there is this carboxyl group here. It may take a minute to do that, and if you need to do that, please go through that after class and do that. However, this reaction is, it's easier to see on this. So our first step, this is an oxidative decarboxylation. Right? Oxidative decarboxylation, reaction 3. Our first oxidative process is going to generate NADH. Right? We're going to assume NADH. It could generate NADPH. It is assuming energy, ATP. So this is going to convert NAD. The first step is going to convert NAD to NADH. Sufficient hydrogen. For NADH using isocitrate dehydrogenase to form an intermediate. This intermediate so we said this was an oxidative decarboxylation. So if it's an oxidative decarboxylation, what am I losing? Carbon dioxide and electrons, right? That's the oxidative part. Oxidative decarboxylation, we're losing 2 things. It's in a stepwise process. What do we lose first? Electrons. We just drew it, right? We lost electrons. So we lose electrons in our first step. And again, this mechanism is shown in your textbook. I'm going to draw to show you how we lose CO2. It's not the old step, there are additional steps. And it helps stabilize an additional intermediate after this, and then yes, there are even enzyme stabilization effects in there in the textbook. Guarantee it's strong. We have CO2 leaves as a leaving group, right? When CO2 is leave, we're going to generate an oxyanion intermediate, so guess what we're going to have something, right? We're going to have something to stabilize it. Is it going to be a metal cation? Is it going to be various hydrogen bonding effects on the enzyme? It's going to be something, I promise you that, right? It is happening. But we're going to have some sort of stabilization effect, right? That's what we're going to have. Some sort of stabilization. This step, we just lost our CO2, right? So first step, we lost CO2, or first step, we lost electrons. Second step, we lost CO2. This is going to leave us with an enol intermediate. I'm not going to draw it. An enol intermediate, right? We're going to have a double bond between these two carbons. It's not stable. So this enol intermediate is going to pick up hydrogen somewhere, either from amino acid or from solution. Hydrogen from solution, and leave us with our oxidized decarboxylated form of isocitrate we call alpha-ketoglutarate. You know, we got 4 minutes left, and we will finish that 4. Start with isocitrate. We'll go through 2 intermediates, an oxalosuccinate and an enol intermediate, and we will left with alpha-ketoglutarate. I will always refer to it as AKG, alpha-ketoglutarate. Alpha-ketoglutarate enzymes are very, very popular, and especially among oxidoreductase enzymes. Alpha-ketoglutarate is commonly a cofactor in many oxidoreductase enzymes. Step 4 is the oxidative decarboxylation. Alpha-ketoglutarate. Use snowflake. So from this information, if we're going to alpha-ketoglutarate, this is single-CoA, and it's oxidative decarboxylation. Give me a guess of what some of my cofactors are going to be. What? NAD plus, right? So NAD plus, yes. Where did this fella come from? Coenzyme A, right? Coenzyme A. Where does it come from? It's not part of alpha-ketoglutarate. It's not part of the enzyme. It's required cofactor. So this is going to require NAD plus and oxidative decarboxylation. It's going to require coenzyme A. This is catalyzed by an enzyme called alpha-ketoglutarate dehydrogenase. Alpha-ketoglutarate dehydrogenase, that's a bad name for it. And this is, you're fixing to see why step 4 is going to take us 2 or 3 minutes to finish. I shouldn't call this alpha-ketoglutarate dehydrogenase. I should call it alpha-ketoglutarate dehydrogenase complex. You're starting to see some similarities here. Guess what this complex consists of? Guess how many different enzymes? Guess how many different? It can consist of a lot of different applied peptide chains, but only 3 different enzymes. Alpha-ketoglutarate dependent dehydrogenase. That's the first one. What do you think the second one could be? Dihydrolipoyl trans. It's not acetylase this time. It's succinylase. Moving a different group, right? And lastly, dihydroxylipoyl dehydrogenase, because we got to regenerate it right back to our step. So if you want a reaction mechanism for this, refer to pyruvate dehydrogenase complex. The first will be the same mechanism. Enzyme 1 does the exact same thing. Enzyme 2 does the exact same thing. Enzyme 3 does the exact same thing. You can imagine these share common evolutionary origins. These two enzymes. It consists of 3 different enzymes, right? Just named them. It consists of 5 different cofactors. Without looking, do you remember the 5 cofactors required for pyruvate dehydrogenase complex? 5 cofactors? How many do you know? NAD, TPP, FAD, LPP, lipoyl lysine, right? It actually, I don't think it's lipoyl lysine here. I don't know what it is. It's a lipoyl group modified to another amino acid. I don't think it's a lysine here, but it's sure lipoyl lysine. That's great. What else? Coenzyme A. I was going to say we just said it on coenzyme A. It also requires coenzyme A. So there are 5 cofactors. I asked you to name 2 at the beginning, so you could see it from the name. We're going to do 2 different things, right? Here's 5. Why? Because it looks exactly like the same mechanism for pyruvate. What's up, man? Look at trans. I'll write that down. That's a good one. Enzyme 2. Enzyme 2 is equal to dihydro lipoyl transsuccinylase. Transsuccinylase, right? We're not removing an acetyl group, or we're not moving an acetyl group, we're moving a succinyl group this time. So it's transsuccinylase, not transacetylase for this complex. That is the only difference. I'm glad you said that. Transsuccinylase. But it is literally the same reaction mechanism. And we will start with 5, 6, 7, 8, and then so Monday we will finish TCA cycle, and we'll talk about and what I like the most is isotopic lead. It's fun. What's up?
What can we expect to guess when this video is posted? What will this lecture be posted?
You have class right now?
Yeah.
You do?
Yeah.
Can you come by right after your next class? Probably 1 o'clock.